All right, everybody, chapter 2. This is the most important chapter. Let's lock in. Busy, gotta go. Okay, so we want a parabola with the vertex this, so that's probably telling us we need vertex form. Vertex form looks something like this. If the vertex is at h comma k, that's what you got. So we want the vertex here, x minus 3 squared minus 4. It's got to be A or C. Now, if we want it to open downward, pretty simple. We need a negative leading coefficient. We need A to be less than 0. So this does not achieve that. That's A equals 1. There we go. Downward. Something like this. Which of the following equations is not a power function? Power function has to be ax to the k, one term, f of x, let's say, equals that, and k has to be, well, k can be anything, can it? Yeah, k can be anything. Just has to be basically, well, it has to be a rational number, I suppose. Actually, the exponent can be anything except 0. Well, I think so. So what do we have here? That's 5. 5 is a rational number. This is 1/2. 1/2 is a rational number. Not that. Let's come back to this. This is, remember, -2. -2 is a rational number. As long as it's x to some power, it's a power function. And it could have a coefficient, but it doesn't have to. This, however, is not a power function. It's an exponential. You need the variable x to be in the base. Okay. Average rate of change. This is just a formula we've got to memorize. Average rate of change from x equals a to x equals b is the change in the output value over the change in the input value. So basically, remember that average rate of change is basically slope, because the change in the y values over the change in the x values. So in this case, we're going from x equals -1 to x equals 3. We could do it thusly: f of 3 minus f of -1 over 3 minus -1. Okay, let's do some work over here. So what is f of 3? Notice I didn't use function notation, but could have just as easily done that. We've got 2 times 3 squared plus 3 minus 3. So that's 2 times 9, so 18. And f of -1 is 2 times -1 squared plus -1 minus 3, which is 2 minus 1 minus 3. -2. 3 minus -1 is 4. 20 over 4. Average rate of change is 5. And if we think about what's happening here, this is going to be some kind of a parabola with a vertex at, the vertex is going to be at -a over 2b. So it's going to be at -2 over 2. It's going to have a vertex at -1 comma -3. So it's going to look something like this. And it's going to have an average rate of change. The slope is going to be positive, maybe 5, something like that. So it checks out, in other words. Memorize the formula. Okay, what are the zeros of this function? Okay, so remember, the idea here is to find the zeros of function, it's best to have factored form. Okay, here we get into the most important section of the year: factoring and polynomials. So let's factor out an x. Okay, keep this other factor like that. And now we've got algebra 1 style factoring. We want two things that multiply to negative 35 and add to negative 2. I believe plus 5 and negative 7 would do the trick. And there we go. This is the fully factored form. I've factored f into a product of 4 linear factors. X to the first, x to the first, x to the first, x to the first. 4 linear factors multiplied together would give us a 4th degree. So each factor is going to give us a 0. X equals 0. X equals negative 5. X equals positive 7 would make that 0. X equals negative 1. So, no, we need 4 zeros. Negative 1, 0, 2, 7, no. Negative 7, no. There it is. Negative 5, negative 1, 0, 7. Find the zeros by factoring. Okay. Now we've got 4 polynomials. Which has this end behavior? Okay, so if I'm given the end behavior, what I would do, I would just sketch it. So this means that as you go to infinity, as x gets bigger and bigger, your function has more and more negative values like this. And as you're going to negative infinity on the left, you also have negative. So it's something like that. Who knows what's going on in between? Maybe it's going up, maybe it's going down. But on the ends, it's going down and going down. That means we know two things. We've got a negative leading coefficient, and we've got even degree. Right, if we've got a positive leading coefficient and even degree, it's going to look like this. However, if we got like a parabola with a positive leading coefficient, if it looks like this, if we got like this, that's what we want. Even degree. Okay. Multiplicity. Okay, so here it's based on a few facts. 1. Zeros at x equals negative 2 and x equals 1 means we've got x-intercepts at negative 2, 0 and 1, 0. Okay, that's clear from the graph. But what must be true if we cross here? That must mean this has odd multiplicity. If you cross the x-axis, it has odd multiplicity such as 1, 3, 5, and so on. So x equals 1 must have odd multiplicity. So it has to be C or D. Negative 2, it's just touching, not crossing, so it must have, I'll say touch, not the K word. So it's must have even multiplicity. Is that enough to get us the answer? No, because these both have even, these both have odd. So how do we get the answer from there? Use the other information in the problem. Degree 5 means, basically it means this. If we wrote this function out, it would be x plus 2 as one factor, because negative 2 is a 0. X minus 1 is another factor. Now there could be some weird lead coefficient going on here, but we know these two have to be factors, and we know it has to add to 5. So, oh wait, hold up. Could be either one. Oh no, this is tragic. This is a problem. I think this is probably the intended answer, but not a great question. I gotta look at that, because technically we don't know if it's 1 or 2, whatever. Alright, I'll look at that, but bad question. Let's ignore this. Which of the following is equivalent to this? Well, we gotta divide. So we could do polynomial division, standard division like you learned in Algebra 2, but let's go synthetic. If x plus 3 is what we're dividing by, then use the 0 of that -3 to do synthetic division. And to do synthetic division, we're just going to put the coefficients. 3, -2, 1, -4. It's going to be faster than normal division because we just got to bring down, multiply, add. Remember to add when you're doing synthetic. Multiply, add, multiply. Oh, sorry, 34 times 3 is 102. 3 times 30 is 90, 3 times 4 is 12, 90 plus 12 is 102. Add. There it is, 3x squared minus 11x plus 34. With the remainder of 106, you put the remainder over the divisor. Okay, here we're using the factor remainder theorem. It says that instead of dividing by x plus 3, instead of doing f of x divided by x plus 3, if all we care about is what is the remainder, we can just plug in the 0 of this. So what I'm going to do is plug in. We need to plug in to find what f of -3 is. And we get -27 minus 2 times 9 minus 7. So we get -81 minus 18 minus 7, which is -99, -106. And what that means, f of -3 is -106. That means if we were to do this division, then the remainder would be equal to some polynomial, but the remainder would be -106. That implies that this does not fit in to f of x. If the remainder is anything other than 0, it's not a factor. That's the factor remainder theorem. You can just plug in the 0 of the factor, or the possible factor, into the function, and the output will be what the remainder would be if you were to divide the function by the possible factor. Okay, rational zeros theorem says if you have a function, it doesn't matter what's in the middle. For this fact, you're just trying to see what are the possible rational zeros of this polynomial. You do the factors of c divided by the factors of a. Factors of c are called the factors of the constant, a plus or minus, factors of the leading coefficient a. So for instance here, d and b cannot have 1/2 because the leading coefficient is 1. The factors of 1 are just 1. So here we could only have plus or minus 1 over plus or minus 1. Or more instructively, here we could have plus or minus 4, 2, or 1. Those are the factors of the constant over plus or minus 1. Only integers. So if the leading coefficient is 1, you could only have integer rational zeros. But the answer is this, because this would have plus or minus 1 are the factors of the constant over plus or minus 1 or 2. So you would have -1, -1/2, -1, -1/2, or +1/2, +1. This could not, because 2 is not a factor of 3, so couldn't have 2 in the denominator. Okay. Now here, What do we have here? How many distinct complex zeros? Well, basically this is talking about the fundamental theorem of algebra, which says if something is degree 4, it's going to have 4 complex zeros. Now, how do I know it's degree 4? Because it's a quadratic factor times another quadratic factor. This is going to be x squared, this is x squared. When you multiply it out, it's going to be x to the 4th. But distinct, this right here, what do we have here? Oh, let's expand it out, or rather factor it out. X minus 2 squared means we have x minus 2 times x minus 2, a repeated 0. X equals 2 multiplicity 2. Now, what is this? How many zeros does this have? Well, this is a quadratic. Again, you learned this last year. We could use the discriminant to see how many zeros this has. The discriminant of this is b squared minus 4ac. It's 1 squared minus 4 times 1 times 1. 1 minus 4 is negative 3. The discriminant, you can use a delta sign for that, is negative. That tells you we've got 2 complex conjugate, or I would call them non-real. Zeros. Because a negative discriminant means you got 2 complex conjugate zeros. We could find them using the quadratic formula, but the point is there's 2 different zeros there. Okay, just one more note on this. So what are the other solutions? Basically, what are the zeros of this? Use the quadratic formula. It's negative 1 plus or minus square root of the discriminant. B squared minus 4ac is negative 3 all over 2. That's 1. And the other one is minus, plus or minus. So we've got 2 non-real zeros, 1 real 0. And so the other detail here is that complex includes real and non-real. Basically, every number you've ever heard of is a complex number. Real numbers are complex, and so are non-real. So we've got 3 distinct, and the real 0 has multiplicity 2. That's how you end up at degree 4, even though there's only 3 distinct. Okay. Chapter 2 also includes rational functions. So, is this a rational function? Yes. A rational function simply has to be a ratio of 2 polynomials. So, remember also, 5x is a polynomial. It's a monomial. You can have a 1-term polynomial, check. And so, of course, is a quadratic trinomial. It is a polynomial. Rational functions don't have to have vertical asymptotes, and the denominator could be quadratic. Okay, but speaking of vertical asymptotes, right, rational functions often do have them, and they're happening when the denominator is 0. So if we rewrite this as its factored form, the denominator, that is, x minus 5x plus 4, it's going to have asymptotes at x equals 5 and x equals negative 4. Because that's where its denominator is 0. Vertical asymptotes are the zeros of the denominator. Horizontal asymptotes, on the other hand, have to do with the end behavior, and we can do it by looking at the leading term of each numerator and denominator. So here we've got numerator and denominator degrees are the same. That means, we need to look at the ratio of the 2 leading terms, which cancel out and give us the ratio of the coefficients, which is 2. That's our answer already. But let's just go through instructively here. We've got degree 2 over degree 2. So it's the same situation. So why is this not the answer? Because now when we look at the ratio, it's just 1 over 1. It's 1. This has a horizontal asymptote of y equals 1. This one has y equals 2. This one you've got higher degree over lower degree. That will have a slant asymptote, which we'll talk about in a moment. And this one has, again, degree 2 over degree 2, so it would be a y equals 3 horizontal asymptote. So for the horizontal asymptotes, compare the degrees. Go from there. By the way, if it was lower degree over higher degree, then it would be y equals 0. Where does this have a slant asymptote? So again, this is degree 2 over degree 1. If the numerator degree is higher than the denominator degree, it's a slant asymptote. And we find it by doing division. Right? We can rewrite this using synthetic division or any division. Use the 0, 1, negative 20. What is the results? It is negative 4. No. It is, okay. Let's do this really quickly. So what do we get here? We get x minus 3, and then the remainder is negative 14 over x plus 2. Remember, slant asymptotes and horizontal asymptotes are basically the end behavior. They're saying what happens as x goes to infinity. As x goes to infinity, this goes to 0. So all that's left is this, our slant asymptote. That's going to be a slant line, y equals x minus 3, that this rational function will approach as x goes to infinity. So for slant asymptotes, you get it if the degree in the top is higher than the degree in the bottom. Use division and just take the quotient, the part without the remainder. Okay, this is basically asking where the vertical asymptotes are, because again, going back to chapter 1, the domain, we just need to have denominator not equal to 0. So basically we're saying x squared plus 5x plus 6 can't be equal to 0. And so we're just like finding the vertical asymptotes, we're factoring it. To make this not equal to 0, we just need x cannot be 3. Oops, mistake, what's my mistake? This is negative 3. We don't want to make the factor equal to 0. So that's it. We're going to have vertical asymptotes at x equals negative 3 and x equals negative 2, which means that you have gaps in your domain. Negative infinity to infinity, but with a gap at negative 3 and negative 2. Solving rational equations, that's a little detail in chapter 2. Okay, let's try to do it as quickly as possible. Want to cancel out the denominators. Multiply by x plus 1. If we do that, we get 3 times x plus 1 over x minus 2 in the first factor. These cancel out. These cancel out. Okay, then we need to multiply to get rid of this denominator. Multiply everything. Cancels out. 3 times x plus 1 times x minus 2. Okay, so obviously next we need to multiply by x minus 2 to cancel out this denominator. And so if we go term by term, this term, the x minus 2 cancels out. This term is just x times x minus 2 because we're multiplying that in there. And then we've got the right hand side. So, how did it get messy like this suddenly? So what we've got here is 3x plus 3 minus x squared minus x minus 2 is, or negative x times negative 2 is plus 2x equals, expand this out, 5x minus 10 minus x squared plus 2x. Okay, apologies for the little bit of clutter here. Let's combine the left-hand side, negative x squared plus 5x plus 3 equals negative x squared plus 7x minus 10. We can add x squared to both sides, so it cancels out. 5x plus 3 equals 7x minus 10. We can subtract 5x from both sides. So we get 2x minus 10 equals 3. Add 10 to both sides. 13 equals 2x. X equals 13 over 2 is 6.5. There's your answer. So, real quick though, because it's a rational function, we gotta check, is this in the original domain? The answer is yes, because the only things not in the domain are negative 1 and positive 2. So that is a valid solution. And once again, we thank Confucius for his guidance. Come on, lock in. Synthetic division. If we divide this by this, we get all non-negative numbers in the last line. What does that imply? Basically, it's not asking us to do this, but if we did this, let me speed run it. Well, what does that tell us? Oh, well, 4 is not a 0 because we got a remainder. But remember what we can look for is, if when we do synthetic division, all our results down here are non-negative, so a 0 is also okay. That means there's no 0 bigger than 4. 4 is an upper bound. That is called the upper bound test. If when you divide with a positive 0, all your results of synthetic division are non-negative, then there can be no 0 bigger than that. So even though it didn't work out, x minus 4 is not a factor, we got some information. We know that there can't be anything bigger than 4. We don't need to try like 8 or 16 or something, because nothing can be bigger than 4. That's the upper bound test. And the lower bound test would be if they're positive, negative, like that. But lower bound test would only work if we tried negative 0. Okay, which has x equals 1 as a 0. So remember, we could use the factor remainder theorem here. We could plug in x equals 1, calculate all of them, see what's 0. But there's an easy way to do that. If we plug in 1, what we're doing basically is 1 to the third, 1 to the second, those just go to 1. We're just adding the coefficients. So a quick way to do this is to just look at the coefficients. 1, negative 2, 1, negative 1. Basically, I am plugging in 1 when I do that, but just looking at the coefficients to do so, well, that's not going to help us. That's negative 1, so no. We get a remainder of negative 1 if we try to use 1 as a 0. Add the coefficients. 2 minus 6 plus 1 plus 3 is 4. Yes, that equals 0. Let's just keep going to double check, make sure I didn't make any mistakes. 1, negative 2 plus 2 minus 7 is negative 6. No, 1 is not a 0. 1 minus 2 plus 1 minus 10 is negative 10. 1 is not a 0. So it's basically using the factor remainder theorem, but that's an easy trick to see if 1 is a 0. Just add the coefficients. Okay, so polynomial inequality, we need to factor it. We need to know when it's equal to 0. So let's go. First thing I'm going to do, factor out a negative x, because every term has x. So that becomes x cubed. and I'm doing negative x because just get this negative out of there. I don't like it. X squared minus 5x minus 3 is less than 0. So I know it has a 0 at 0. So something's probably going to be involved with 0. But I need to continue factoring. So what are the possible zeros? It's going to take longer than I thought. Well, the possible zeros are the factors of the constant are just 1 and 3, and the factors of the leading coefficient are just 1. So therefore we have a plus or minus 3 or 1. Okay, that's easy. So we've got negative 3, negative 1, 1, 3. Okay, not too bad. So let's see. We're going to do some synthetic division just for this. 1, negative 1, negative 5, negative 3. What are we going to test? Well, let's use our trick. If we add these up, add all the coefficients, you get negative 8. So 1 is not a 0. But watch this. If we add the odd degree coefficients, you get negative 4, and you add the even degree. If the odd degree coefficients add to the same thing that the even degree coefficients, that's another trick that tells us negative 1 is a 0. And so we already knew 1 was not, because it doesn't all add up to 0, but negative 1 is. And if you didn't know that trick, you can always just check and you'll find out. Okay, so let's do synthetic division. 1, negative 1, add negative 2, 2, negative 3, multiply. There you go. So negative 1 is a 0. So let's say we got negative x plus 1. Then we've got x squared minus 2x minus 3. And this can be factored as negative 3 and plus 1. So we've got multiplicity 2. So we've got, let's do them in order. Negative 1 has multiplicity, well, let's just do it like this. Now let's do that. Negative 1 has multiplicity 2. 0, multiplicity 1, and 3. So if we were to sketch this, plot the zeros, negative 1, 0, 3. Doesn't have to be to scale, just in order. Now go back. We've got degree 4, negative leading coefficient. That means we know the end behavior. Degree 4 negative leading coefficient is even degree negative leading coefficient. We know it's downward like that. Now we can use the multiplicity to see what's happening in between. And negative 1, since the multiplicity is even, it's just touching the graph. At 0, the multiplicity is 1, which is odd, so it's crossing. And at 3, it's also odd. So there's a sketch of our graph. And if we want to know where it's less than 0, strictly less than 0. Ah, Lord, I think I need another mistake here. Well, let's just keep going. Here we go. Oh, no, this is correct. Very good job by me. Here it's negative. Here, from negative infinity to 0, but not at negative 1. At negative 1 is equal to 0. We want it strictly less. And then from 3 to infinity. Yes, no mistake. Okay. And then here, okay, let's go quickly. This is the same concept, but it's a rational function. We need to just check two things. One, the vertical asymptotes, x equals 2. 2, the zeros of the function itself are the zeros of the numerator. If you plug in negative 3, you get 0 over negative 5, which is 0. So we can use the same concept to say, okay, at negative 3, something weird is happening. Well, not weird, but important. It's 0. At positive 2, something important is happening. It's a vertical asymptote. We just need to check in between. So we can check by plugging in something over here, like let's check x equals negative 10. That's to the left of negative 3. At x equals negative 10, you get negative 7 over negative 12. You get a negative over a negative. That's positive. So that's not going to satisfy because we want it to be negative. It'd probably be looking like this. Then at negative 3 it's 0. Then in between it's 3 over negative 2. 3 over negative 2. It says positive over a negative. So it's negative. It's probably doing something like this. And that's what we want. We want it less than or equal to 0. So it's not going to be this because it is 0 and negative 3. And it's not going to be these ones either. We already know the answer because it's not negative over here. But let's just check for completeness. If we plug in something big like positive 10, we get positive over positive. Positive over positive is positive. And so it's not less than or equal to 0. Beyond 2, it's probably something like this. So our answer is this. At negative 3, it's equal to 0, then it goes negative, hits a vertical asymptote, never reaches. All right, local extremal question from a polynomial. So what do we got here? Well, basically, just looking at the graph, it appears we have a local max, local min, should be 2, and what else can we tell? Well, if these are the only zeros, we know that it shouldn't, the end behavior is going like that. So, I don't really know if this question is that deep. I think it's just too local extrema. Okay, let's go on to if x minus 1 is a factor of this polynomial, what's the value of k? Okay, I think again this is a perfect one for factor remainder theorem. We could do some division with this, but I think it's better to say, well, let's call this f of x, and let's plug in the 0 of this factor x equals 1 and see what we get. K times 1, just replacing all the x's with zeros, of course. 1 minus 3 plus k. And if it is indeed a factor, remember the factor remainder theorem says it must equal to 0 when we plug in 1. So this has to equal 0. Negative 2 plus k equals 0. Therefore, k equals 2. Again, you could use synthetic division here or something and go from there, but this is probably the quickest way to do it. Okay, this appears to be a end behavior question, right? Because we're asked about the degree and the leading coefficient, and we've got end behavior that appears to be going to infinity and infinity. So it should be even degree because both the limits are the same, and it should be positive leading coefficient because it's going upward. I would change that to leading coefficient, just that's a small detail. Okay, almost to the end here. Another question about upper bound theorem. So we're dividing using 3, so we're checking the factor x minus 3 or the 0, 3. The fact that we get something non-zero here means that in fact it's not a 0. We're getting a remainder, right? We're getting 2x cubed plus x squared plus 10x plus 27. But the fact that we get all non-negative means there cannot cannot be anything bigger than 3 that is a 0 of this function. That's what the upper bound test says. Okay, and last question, short answer. For the function f of x, x equals 2I is a 0. Y equals f of x has one x-intercept at x equals at 3, 0, so that means x equals 3 is also a 0. And the function has degree 3 and the leading coefficient is 2. It was kind of weird that I wrote the word out 2. Write a function f of x that fits the description. Okay, so basically what do we know? We know that it's degree 3. So we know it should have 3 zeros if we count multiplicity. Now, we know 2 of the zeros. Right, again, what this means, if you're crossing or you're touching the x-axis at 3, 0, that means x equals 3 is a 0, because f of 3 is 0. So we've got, might seem like a couple possibilities, because what if this has multiplicity 2? Then we could still get to degree 3. But remember something important. If a function has 2I as a 0, the conjugate must also be a 0. So that would be our third 0, and that would leave us with our degree. So we can say our factors are x plus 2x minus 2I to match these two zeros, x minus 3, and we can expand. X squared, same thing, square it, opposite things, square it. And it's going to be times x minus 3, so it's x squared minus 4I squared. I'll just write it out to be careful. And by the way, we're going to need a leading coefficient of 2, so tack that on there, because we're only going to get it if we have that there. So we've got 2 times x squared. This becomes negative 4 times negative 1 plus 5 x minus 3. I mean, technically, already we have what we need, but let's put it in standard form. F of x equals 2x cubed minus 6x squared plus 10x minus 30. That should do it. And we finished off chapter 2. We've got vertex form of a parabola, power functions, average rate of change formula, factoring polynomials to find zeros, end behavior, multiplicity of zeros, synthetic division to find zeros, factor remainder theorem to find zeros, rational zeros theorem, the fact that the degree tells you how many zeros you have, including non-real and repeated zeros. We've got rational functions, vertical asymptotes, horizontal and slant asymptotes, factoring to solve polynomial inequalities, upper bound test, and remember that if one non-real zero exists, a complex conjugate has to be there. Alrighty, go blue.